Hello and welcome to another episode of Math-Adda. I'm your host Shankhadev. Today, I'm going to talk about something basic in the sense which is which at a first glance does not appear to be very sophisticated, but it is very important to all of mathematics. What is that? Set theory. Now, here is something that I say very often. Mathematics is structured like a building. Okay. One layer is constructed on the top of the previous layers. Okay. If you consider mathematics as a building, the basement or the foundation of that building is set theory. Everything comes from set theory. Okay. Sets Set theory basically means the definition of the concept of a set and the ZFC axioms, Zermelo-Fraenkel choice axioms. Those are the axioms that tell you how to manipulate sets, how to take unions, how to take intersections, how to take Cartesian products, all that. Everything that you need to know to manipulate sets is contained in set theory. From set theory comes the concept of zero. From there comes the concept of natural numbers. From there comes the concept of integers. And from there comes the concept of rationals. From there, R. From there, C. And so on, many other things. But everything starts from set theory. Okay? That's why I say that it is very important. And we actually in school, at least in India, we learn set theory only late. At least I did. I learned set theory in 10th or 11th standard, and there's no reason for that. At least the basics of a set, the definition of a set, the symbols like belonging to, intersection, unions, those things can be taught earlier. Okay. And there are some things that we are taught, but we do not realize the importance of. One of them is the concept of a relation. Usually, in set theory, we learn about sets, we learn about relations, and from there, we directly go to mappings. Mappings, or in other words, functions. Because functions are important functions, we use functions in calculus, etc. Nobody tells us why we define relations in the first place. Why not go directly into functions in some way? Okay. I will give you an answer to that today. What is a relation? Given two sets A and B, a relation on A times B is a subset of A cross B. By the way, A cross B is the Cartesian product of the two sets. In set builder notation, it is defined to be that of all A comma B, base A comma B, says that small a comes from capital A and small b comes from capital B. Any subset of this is considered to considered to be a relation. Suppose we have a relation R. If A comma B is in R, we say that A is related to B. And then you probably remember that a function is a relation such that every element in capital A is related to some element of capital B, and actually it's related to exactly one element of capital B. One element of capital B can be related to multiple elements of capital A. I mean, one element of capital B can come from multiple elements of capital A, but not vice versa. In for the case of a function or for the case of a mapping. Now, you probably also remember that there is something called an equivalence relation. What is an equivalence relation? Before we get to equivalence relation, we have to talk about reflexive, transitive, and symmetric relations. Reflexive. By the way, when we talk about equivalence relations, A is equal to B. Okay. So the set we are talking about is A cross A. Suppose we have a relation R on A cross A, then it is said to be reflexive if A is related to itself for every small a. It is said to be transitive if A related to B and B related to C implies A is related to C. And symmetric if A is related to B, if and only if B is related to A. If a relation satisfies all three, it is called an equivalence relation. Why is this important? You have probably seen this in some school book, but there was no explanation. There was just a definition. Hey, this is an equivalence relation, and that's all. Today, I'm going to tell you why equivalence relations are important, why we define such relations at all. The thing is, when you have an equivalence relation on a set, you are able to partition the set into a number of subsets which are disjoint. Those are called equivalence classes. It's like if we have a symmetric relation, an equivalence relation on A, then A can be written as a disjoint union. By the way, this is a symbol of a disjoint union. Some A alpha. So it's a disjoint union of some subsets such that if X, Y both belong to A alpha, then X is related to Y. And if X is in A alpha and Y is related to Y is related to X, then Y is also in A alpha. In other words, each subset A alpha contains the elements which are related to each other. So all elements in some A alpha is related, the elements are related among themselves, and no element in A alpha is related to some element in A beta. Okay? Those are closed groups. You can think of them as families. These families have no interaction with other families. Each A alpha is a family. And I will give you some examples of this. But before we get there, let me tell you why this is useful. Once we have such a decomposition, we can construct something called a quotient space. And it is sometimes denoted as A, like this, R. What is the quotient space? Is the set of all such subsets. By the way, this I is an indexing set. Okay? It could be a finite set, it could be N, it could be R, it could be anything. So the quotient space is a set of sets. It's a set of subsets of A. And why are quotient spaces important? Quotient spaces are seen all over mathematics. This is a construction that allows us to construct new spaces from given spaces. Let me give you our first example. Actually, we are going to discuss only 3 examples, let's say. Example 1. N fix. Actually, well, let's make it Z. No, don't need to make it N. Fix some number N, some integer N. Let's make N a positive integer. And introduce the equivalence relation. A and B integers are related if and only if N divides A minus B. By the way, the relations we are going to discuss are all equivalence relations, but I'm not going to prove that because it's very easy. I will leave it to the viewer, viewer to check. So this is actually an equivalence relation. And what are the classes, equivalence classes of this equivalence relations? This equivalence relation? The equivalence classes are precisely the integers that have the same remainder upon division by n. And by the way, I forgot to mention something. Sometimes we represent an equivalence class by just one element, because from one element we can find all the elements related to it and we can put them in the class. Okay, we call such an element a representative. So what are the equivalence classes here? The equivalence classes are the class of 0, the class of 1, the class of 2, up till the class of n minus 1. 0, this actually contains 0, n, minus n, 2n, minus 2n, and so on. This contains 1 plus minus n plus 1 plus minus 2n plus 1, and so on, like that. Therefore, the quotient space is 0, 1, this. This particular quotient space is also known as Zn or Z by Nz. You probably noticed that this is actually the same as the class of complete residues of n. This is our first example of a quotient space. From here, in this example, we have constructed a new space, which is a quotient space, but it's not very interesting. The second example should be more interesting. R. A and B are related if and only if A minus B is an integer. The question is, how does the quotient space look like? Obviously, you can give an abstract description of the quotient space, but that's not very helpful. We are looking for a model that would help us visualize the structure of this quotient space. Let's begin. First, note that given any number x, any real number x, it can be written as a sum of the integer part plus the fractional part. And the fractional part lies between 0 and 1. Therefore, x minus the fractional part is an integer. Hence, x is equivalent or related to its own fractional part. Note that this means every real number is related to one and only one element of 0, 1. Let me write this down. Therefore, the line segment 0, 1, 0 is included, 1 is not. This is a good representation of this quotient space. But we can actually do better. Why? See, most elements in this set, the most elements that are represented here belong to distinct equivalence classes. But 0 and 1 are actually in the same equivalence class. I mean, at the level of the quotient space, 0 and 1 are the same. So our model should reflect this fact. Looking at this model, you do not know that 0 and 1 on the are uh, in the same equivalence class. You should make a model that reflects that. How? By putting the two ends of this line segment together by hand. So just imagine if it's a string, it's a piece of string, and put them together, and what do you get? To put the two ends together, you get a circle. This point is 0 or 1. Doesn't matter, they're the same. Therefore, R quotiented by this particular equivalence relation is the same as the circle S1. S1 simply means one-dimensional sphere. Okay? So we have, starting from R, we have constructed S1. We have discovered a new space. Now let me give you another example, which is even better. Consider R2 and A comma B is equivalent to or related to C comma D if A minus C is in Z and B minus D is also in Z. By the way, you have to prove that, you have to check that all these relations I'm talking about are equivalence relations. But that's very easy to check. And the proof is exactly similar. You prove that A comma B is actually equivalent to fractional part of A comma fractional part of B. Therefore, every point in R2 is represented by exactly one point in the square. But again, this representation misses things, that some of these points are actually equivalent, and our visualization should reflect that fact. For example, x comma 0 is the same as x comma 1 for every x, or the yellow parts, the yellow line segments I drew there, they're actually equivalent. And similarly, 0 comma y is related to 1 comma y for every y, or the green parts, the green line segments are actually equivalent, they are the same. So we have to modify our model a little bit to reflect that fact. How do you do it? How do I do that? First, I bring the two yellow edges together. What do I get? I get a cylinder. And see, this yellow edge is where I sew them up. Okay. Now, it's still not complete because I have to bring the green edges together as well. And when I do that, what do I end up with? I end up with a donut, which in mathematical terms is actually a torus. So there will be a green circle here where I join the two circles, two green circles, and there will be a yellow circle like this where I join the two yellow circles. Therefore, this quotient space is a torus. R2 quotiented by this equivalence relation is T2. T2 means the two-dimensional torus because there are higher dimensional tori as well. And T2 can also be shown to be a product of two circles. Can you show that T2, the torus, is a product of two circles? If you can, please leave your proof in the comments. So this is how quotient spaces can be discovered, can be used to discover new spaces from given spaces that we already have. And there are more. There is something called a projective space, which is something you can't even imagine, but it exists. It goes as follows. Example number 4. Again, start with R2 and identify lines. How? Every point A comma B is identified or with lambda A comma lambda B, where lambda is a non-zero real number, or A comma B is identified with C comma B if A by C is equal to B by D equal to some constant. What is this doing? Suppose this is R2. it's turning the lines, except the origin, of course. Origin has to be considered separately. It's turning the lines into equivalence classes. So if you consider the equivalence, the quotient space created by this construction, in that quotient space, every line is a point. I know it's very hard to imagine, but it's hard for everyone, so don't worry. And there is a way to visualize this as well. How? Draw the unit circle. Note that every line passing through the origin cuts this unit circle at two diametrically opposite points. Therefore, every diametrically opposite point corresponds to every set of diametrically opposite points corresponds to one and only one line passing through the origin, and therefore one and only one member of our quotient space. So instead of considering lines, I can now consider diametrically opposite points. Let's get rid of the lines. As we are constructing a model for our visualization, we can take some liberties. We can say, look, instead of diametrically opposite points, I can take just one of the points. Why? Because the lower hemisphere, this one here, it is just a copy of the upper hemisphere, right? It's because corresponding to this point, you have this one. Corresponding to, say, this one, you have this one. And you do not need both in order to visualize. You can have just one. So let's get rid of this lower hemisphere. And now you have just the upper hemisphere, and you have one representative of each equivalence class. But there is a catch. There is one equivalence class which has two representatives in our model. Which one is this? This one. These endpoints. They belong to the same equivalence class. So as before, how do I get rid of that? How do I construct a model which reflects the fact that these two endpoints are actually in the same equivalence class? I bring them together. Physically, I imagine imagine that it is a string, and I bring the 2 points physically together. What do I get? In a circle. So this is another way of constructing the circle, starting from R2. No, in the first proof, I started from R and found a circle. But here I started from R2 and found a circle, constructed the circle. So R2 quotiented by this equivalence relation is actually a circle. Now, all the spaces we have seen till now are actually spaces that we already knew before, right? We knew the circle before, we knew the torus before, we knew Zn before. So you might think, what's new here? I'm just rediscovering the same things that I always knew. That's not the case. I will show you something that we did not know before, and we discovered via quotient spaces. Take the example given in 4 and apply it to R3. In R3, we identify A, B, C to lambda A, lambda B, lambda C. In other words, in the three-dimensional space, we are identifying the lines, our equivalence classes are lines passing through the origin. It's very similar to the case we just discussed. Okay? So each line passing through the origin is an equivalence class. As before, we can draw a sphere, a unit sphere, about the origin. And each such line intersects the unit sphere at exactly two diametrically opposite points. So instead of considering lines, we can consider diametrically sets of diametrically opposite points on the sphere. And just as before, we do not need the lower hemisphere because it's just a copy of the higher upper hemisphere. So we can reduce our model to just one hemisphere, say the north hemisphere, something like this. But just as in the previous case, there is still a problem with this model. What is that? There are some points that belong to the same equivalence class. This and this, for example, these two diametrically opposite points. Then these two diametrically opposite points. And our model should reflect the fact that there are points that are actually in the same class. And how do you do that? We try to physically bring them together. So we have a hemisphere, and it has a base, which is a circle. And we have to somehow bring together each set of diametrically opposite points on the circle. That cannot be done by humans, right? But in the mathematical world, it can be done, but it's impossible for us to visualize. Such a space exists. It is called the real projective space of dimension 2. Why does it have dimension 2? Because you can see from this part that it's a part of a sphere. A sphere is two-dimensional, so it's two-dimensional. But it's a space that we did not know before. We started quotienting, and we discovered something new. And it's so complicated that we can't even imagine it. Okay? So this is one of the reasons the quotient construction is very, very important throughout mathematics. And this is why you should pay more attention to set theory. Okay? That would be all for today. Take some spaces and try to discover some new ones. And let us know if you come up with some interesting spaces. That would be all for today. Bye-bye. See you next week.